Hi everyone. I'm going to talk about the architecture of our cloud database service and how we were able to launch it in a very quick amount of time. My name's Will Leinweber. If you want to get in touch with me afterwards, Leinweber on Twitter. Company I work for is called Citus Data, and if you are a fan of 90s websites and MIDIs, my website, bitfishing.com, is the place to be. For those of you who are in the Postgres community, we have a conference coming up in November. Check that out. So for this talk, I'm going to go over what makes Citus different than just normal Postgres, because the differences there informed a lot of the decisions that we made when building the cloud service. I'm going to go over the origins of the service, introduce some concepts, and share what things worked surprisingly well. There's a lot of things that goes on in the service. I think the important ones are the ones that you're surprised about that tend to work better than they seem that they should work. We're going to go over disaster recovery, a little bit of a rant on microservices, and other interesting things that we've learned along the way. So Citus Data is an open source Postgres extension that lets you scale out Postgres. It takes care of all the sharding, the parallelizing the queries, distributing things to the right nodes, while still giving you the same data structures and SQL coverage that you would expect from a nice database like Postgres. So many apps eventually outgrow single node Postgres. You can always scale up your database to bigger and bigger hardware, but on Amazon you reach a limit point pretty quickly. You can go a little bit further on bare metal hardware, but even then you're going to start to run out of headroom on single node Postgres, and then you can mitigate this by deleting old data, by trying to keep your data set small, but that is, like a Sisyphean task. Like you're always, I was in that situation trying to always get rid of data that was, just kind of sticking around, but eventually you just need to shard out into multiple databases. You can do this yourself by, having a shard key in your app and talking to the right database, but having Citus do that for you is a big advantage. So this isn't a Citus talk, so I'm not going to spend too much time on this part, but it's important to understand. So when writes go in, they pick the correct node to do the insert or update by looking at the hash key. And there's two sort of ways that people tend to use Citus to model their data. One is in this sort of parallel model where it takes advantage of distributed query planning. And so when a query comes in, it ends up hitting all of the nodes, does the computation on each one of the nodes, and actually for each CPU core that you have on each of your worker machines, it'll make a separate connection for each one of those, and so you can take advantage of the distributed CPU power of your entire cluster. And it then aggregates all the data and returns it to the client. But because it's hitting all of the nodes, any sort of SQL that needs to have data communicate between those different nodes either works slower than you'd want, or we block it out. And so this is more of a use case for customers that would need to move to something like Cassandra or React or Dynamo. This sort of is a replacement for having to do that big of a move. You're going to have to rewrite some parts of your app, but it's a lot easier than going to a completely different database paradigm. But the advantage is you can use all of your cores. I was talking to this one group of people that, with almost the same spend in hardware, was able to get a 200 to 300% or 200 to 300 times increase in their query performance because it was like a CPU-bound task. The other model that seems to work very well is sort of this multi-tenant model, where every single query that you put in has a where clause, like where organization ID is 10, or where tenant ID is 5. And in this case, Citus will just route it to one individual server and get the data back. And as long as all your tables are sharded in the same manner, it just looks like a regular Postgres node. And so in this way, you get all complete SQL coverage. And this is probably what more people think about when they think oh, I'm going to need to shard my database. They're going to make copies of their tables on every single node, and then route the query in the application layer to the right database. And that's, of course, always doable. People have been doing that for a long time, but having your database handle that for you is kind of nice. Because Citus is open source, you can go ahead and run it yourself, no problem. But there's a lot more to managing a fleet of Postgres instances than there is to running just one by yourself. And those differences we're going to get into in the rest of the talk. But it, just as an overview, it's things like you need to set up disaster recovery for each one of them. You need to make sure each one of them is patched. Make sure that if you're doing streaming replication, that they're pointed at the right thing, and so on and so forth. And so because of this, a couple of months ago in February, me and a couple of people were hired to build a hosted service for Citus so that customers of Citus wouldn't have to set it up themselves. But there's trade-offs for that, of course. One of the upsides is my team can spend a lot more time on automation than individual people can or probably should. Your time is probably spent better on your application rather than the infrastructure and automation around that. The other thing is we see many, many, many more edge cases than an individual might see. I'm not sure if this is an appropriate analogy, but when I was thinking about this, it reminded me of one of my statistics courses in college. I forget exactly what it was for, but the analogy kind of stuck with me that if you're on a golf course and you are a blade of grass, and the ball hits you, you think, oh, geez, like what were the chances that I would, if all these millions of blades of grass in the golf field, that it would hit me? And that's true. Like, you will never, it's really rare that you're going to have a catastrophic event. But that golf ball is going to hit some blade of grass. Like someone's going to have a bad day. And by running this service, being on the receiving end of that, I see all these different ways that things can fail and have more of the motivation and impetus to automate these kinds of failures. The downside, though, of course, to you putting your data in a hosted service is loss of control. Like when you are down, your service provider is scrambling to fix it, but you often don't have all that good insight into what they're actually doing at that point of time. And so that can feel a little, that loss of control can feel a little bad. So the origins of this cloud service actually goes back much longer. Me and a couple other people ran the Heroku Postgres data service where we had millions of databases on a very small team of, I think when I left it was 8 or 10 people. And we took a lot of those same learnings over to us when we made the data service for Citus. And I can't overstate the confidence that gave us, having done it before, allowed us to move quickly and with a good direction. The other part is knowing what tools worked well ahead of time, not having to discover them. And the other part that I learned, not so much on the technical side, but from the product development side at Heroku, was that being ruthless in cutting scope is a lot more difficult than you often read about. Everything you read about, it's like, oh yeah, you can either cut scope or increase the budget or whatever, and people kind of pay lip service to cutting scope. But seeing teams at my previous job that actually did cut scope and other ones that talked about it, it seems that if it doesn't actually hurt, if you need to drop this feature but it pains you to do it, then that's actually cutting scope. And to launch our cloud service here, there was a lot of things that we cut that really did hurt. But the parts that worked well, that I wanted to keep using, there's a framework for Ruby called SINATRA, and more importantly, the ORM called SQL is just phenomenal. I haven't seen a software project run better than SQL. The maintainer releases a new release every single month of just incremental changes. And so there's never a big version X.0 that you have to scramble and do a lot of refactorings. As long as you kind of keep up to date over time, everything works really smoothly. And unlike a lot of other ORMs I've seen, you can really use advanced Postgres features without problem. A lot of other ORMs that I've seen, Active Record in particular, tends to kind of lowest common denominator between all the supported databases. Where in SQL, it seems like it's sort of a Postgres first and then other databases second kind of thing, which I like. But the biggest reason I stuck with using Ruby again for this is the interactive console. There's a lot of times where something small is on fire, and being able to isolate that in the console and work with the same domain models during development to go and fix it is just a huge time saver. For example, there's a situation where there's a bad point release of some library on the machines, and being able to filter through everything that was running, find those small handful of machines, and then issue background jobs to go SSH in and fix it was so much easier than, I don't know what else we would have done. Maybe write some PDSH thing to SSH and everything and check, but having this interactive console and having it be one that isn't white space sensitive, that is easy to hack around when things are on fire, has been a lifesaver time and time again. One model that has worked extremely well is keeping the servers that run the databases mostly immutable. So we always prefer throwing away an entire database server after having replaced it with a fresh one, rather than go in and fix things on the fly. Because when you start just patching over problems, you end up like this probably not great to walk under support beam. So the other nice thing about this is, because the servers are sitting there and running, it's always when you go in and change something that you cause downtime. And so by leaving the servers running, even if they, we could in theory patch them on the box, it's much, much, much more robust. We'll touch a little bit more on how replacements actually work under the covers later. The other thing that is sort of the key core concept is this sort of outside-in checks. And so rather than having an agent run on the box that is doing health checks and reporting out, we have a central service that every 10 to 30 seconds connects over pSQL to make as if they were the customer, to make sure that the database is up and running from a customer point of view, and also SSHs in and does health checks that way. It is very robust, but it is inefficient having to establish those connections all the time. But I think the inefficiency is worth the other things. And one of those things that it gives us is when we need to start doing new checks, when we want to modify how we're doing these health checks, we just change it in the central application, and it starts dialing out with those new checks, rather than having to go across the entire fleet and update software on every single one of the machines. So now I had to sneak in a little bit of a rant on microservices. This has been sort of like a buzzword for the last year or two, and I saw a lot of this of people spinning up their own small service, and sometimes spinning off services is the right thing, but I think it's been reached for a little bit too frequently. Sort of as a side, this isn't a new concept, Conway's law, but that organizations, the systems they design tend to reflect the communication structures. And when I first heard about this law, I don't know how long ago, I thought at first this is something that this shouldn't be. Like, the system should be designed as systems should be designed. Let's disregard the communication structures. I thought this was something to fight against. But I've now come to the opinion that this is inevitable. And rather than spend effort fighting against it, sort of just know that that will happen and try and make it not as bad once it finally happens. The upsides of microservices is that you can sort of have things isolated, but the downside is now if you want to figure out what's actually going on, you can't just look in one database and do a couple joins. You have to make API calls across all these different apps. And while it is true that each individual app may be simpler, all the complexity has now been pushed into the channels between the apps, and that's really hard to reason about and debug. That said, our current service is made out of two separate services. One that is the external user-facing dashboard of metrics and provisioning and so on, and the other one is the internal control plane that does provisioning. And this, I think, makes sense because operationally they're very different. The UI, the customer one, has very low throughput. It's just when customers log in and click around, whereas the control plane is constantly doing health checks and so on. So the console is, the UI is the primary thing that it's responsible for. Also, it takes care of billing. It takes care of the users creating and managing their formations. And this one is in Ruby on Rails, but then we replaced Active Record with SQL. And the control plane is the SINATRA thing from before. And this does all the monitoring, all the healing, and this will be the focus of the remainder of the talk. The commonalities between the two, of course, are the Ruby language and the SQL library. Before we go further, we need to introduce a couple of the building blocks that I'll be mentioning with the control plane. And the main things is the relationship between a formation and the servers. So a server is an AWS instance. These are the things that are actually doing the work. A formation is the logical grouping of those instances that make up what the customer thinks of as their database. Over time, this is decomposed into other pieces. There's timelines, which we'll touch on, and other helper models, but these are the core concepts. But one of the things I've learned over time is that AWS is it seems like it's actively hostile against you. And so because of that, the number one thing that I worry about is data protection. Over availability, over uptime, data protection is job one. If there's a bug in your application and your site's down, that's one thing. If your data is corrupted or missing, that's a situation where now your business is in trouble. Downtime is not great, but corrupt and missing data is far, far worse. And so this is a tool that's been around for a while now, written by my colleague, and it takes Postgres write-ahead log files and ships them off the machine. And so for those of you not familiar with Postgres, the way that it works is as every write comes in, every modification, the write-ahead log captures the physical changes that would happen for that data. And we have it set so every 16 megabytes of accumulated change or 1 minute on wall clock, whichever happens first, the wall file is finished, and then we send it off of the machine to Amazon S3. And S3, fortunately, has been pretty much rock solid. And because now that we have the data off the machine, that machine can melt down in a fire. It can just vanish into another plane of existence, and I don't care. Because while that would be downtime, I now have the ability to replay up to that 16 megabyte or 1 minute window, which is often a very small window of potential loss. And the good thing is it's always consistent. The other step here is every day we kick off a base backup, which is a sort of freeze-dried thing of the entire database, and then the wall files can replay off that point of time. And so this is good for a couple of reasons. We can do point-in-time recovery in the past, if there's any sort of instantaneous problem that the customer sees, and we have this always continuously protected database. And at first, we just kind of, didn't have a model for it. But then we realized that things were getting cumbersome, so we created this concept of a timeline. And the big diamonds there are those base backups, and the blue is sort of the data going forward. And so this represents the progression of data over time as time progresses. And with that in place, we can create read replicas with a good model. And so a read replica is on the same timeline, but it is read-only. And so the nice thing about Postgres is that we can spin up a new read replica by pulling off the most recent base backup and start replaying the wall. And then once it gets caught up close enough, it switches into streaming replication and it just pulls the changes as they come in from the leader database. If anything happens were it to fall behind too far back so it can't do that streaming replication, it'll automatically switch and start pulling those files off of S3. And so this works as a great way to fan out read replicas. And so if in a couple of situations where we need to do a changeover or failover, what happens then is one of those followers gets promoted to be the primary. We create a new timeline, and it starts a new timeline and a new base backup, and then everything can proceed from there, and we cut off the old one. And there's a couple different reasons that we do server replacement. One is the obvious one with failure, but that's actually doesn't happen as often as the other reasons that we do replacements. Because I mentioned earlier that we have this sort of philosophy of mutable servers, when we want to do something like changing the disk layout or some sort of critical sorts of upgrades, especially with bigger versions or newer versions of Postgres or Citus or operating system versions, it's easier to use the same mechanism that we have in place for disaster recovery and reuse that mechanism for this sort of controlled replacement. And there's a lot of benefits for that. Because it's the same mechanism in both cases, it gets tested much more frequently than failure modes get tested. And it also keeps all the edge cases in code down to a minimum number of changes. And I think the only real difference is how it enters the replacement mode, if it's something we're scheduling or if it's something that automatically happens. And while it can take a little while to prepare a follower to download the base backup and get it consistent and caught up, the actual changing over is a matter of seconds. What we do is make it so that it's a read-write database, create a new timeline for it, and then move the elastic IP over. And then clients can reconnect to that database, and it is as if it's the new master. In the meantime, we're doing several different ways to shoot the other node in the head. We're telling Amazon to destroy the instance. We go in and we turn off the networking from it. And then also the act of ripping the elastic IP off of that machine. All those things together, and I think I'm leaving out one or two, is really important because one of the worst things that can happen is that sort of split brain scenario where you have some clients writing to the old one and new ones writing to the new one. And so having a lot of redundancy in the way of shutting off the old, either failed or controlled failed primary is very important. One of the things that I think is an interesting aspect that we have in this is sort of something that came together from one of my former coworkers and bosses' time in the video game industry. And it's one of the things that works surprisingly well. That's going to get there. No. Sorry about that. And what this is this sort of feel and tick model. So in the video games that my colleague worked on, what would happen is all the items on the screen, all the monsters, all the player character and everything, would observe the entire state of the world and then make decisions based on that and move their state. And then repeat that over and over again as the game progressed. And this actually works really well in writing a service for Amazon. And because things change out from under you. A server that was working just fine minutes ago now is completely inaccessible or suddenly forcibly retired. And if you sort of if you don't do this constant observation of what is actually true, you'll be led astray very quickly. And so we have all these state machines to manage our infrastructure. And so when we're creating a new machine, it's in the creating state. Eventually, everything's online, SSH is up, Postgres is booted. We observe that happens, and we move the state over into available. Then it can go to become deprovisioned, and then we do the work of destroying it. But if anything happens, and we notice that I can't connect over SSH, or SSH is timing out, or I can't connect in Postgres, or something weird goes on, we move it into an uncertain state. And then if it stays in that state for a period of time, say a minute or so, then we'll kick it off into unavailable and start doing the recovery. The reason for this is we've seen a lot of times where it's just some sort of network blip that causes this unavailability. And were we to be trigger happy on doing failover, we would be doing it much more frequently and actually cause more downtime than having this sort of uncertain state where it might be offline, it might not, we're not really quite sure yet. And while that does increase the time to recovery for cases where it's actually offline, because there's so many of these sort of false flags, this, I think, increases our aggregate uptime. And the other thing with these state machines is we're always converging to trying to get into a new state, a better state. For example, there was this, in January, there was this Amazon outage, and we needed to pull all of the elastic IPs that were affected off and then put them back on. And we could have, this is a situation that we never had seen before. And being able to, instead of having to write the code to detach them and make sure they get attached right, the state machines were written such that if the elastic is gone, that's sort of an error case and it goes to converge and reattaches itself. So all we had to do to fix that was just disassociate the IPs, and then the state machines, as they continued to work to converge, brought everything back. And so that worked extremely well. And so we have all these state machines working. We need to make sure that they get scheduled correctly. We need to make sure that they get a fair amount of time to run and do the work necessary. And the way we do that is a really great library called SIDEKIQ. I've looked at a lot of different libraries over the last several years. We've moved around from like in-house written ones to a couple different ones that I can't think of the names off the top of my head now. It's been a while. But SIDEKIQ has been really great. Redis is the background database that holds it, but it has really good concurrency support where even in Ruby without single-threaded runtime, the concurrency, it can spin off these different things. And because most of what we're doing is waiting on I/O over SSH or waiting on I/O over Postgres, we actually get a good concurrency despite that. And another nice thing about SIDEKIQ is that the client libraries are now in several different languages. And so if you want to enqueue a job from one and have another language do the work, that sort of now is working seamlessly. We're not taking advantage of that quite yet, but one of the languages that I've actually been contributing to, Crystal, has a SIDEKIQ library, and that may prove to be a good avenue going forward. That said, though, having this sort of model of putting the jobs in a queue and then working them has caused a few problems. The first way that we tried this was having the jobs themselves re-enqueue themselves. So like if server 1 does its health check, it does the health check, and then re-enqueues a job itself to do server 1's health check again. And this was simple, and we thought it would work well. But we started seeing some problems where if something would blow up in there in such a way that for whatever reason wasn't recoverable, like a simple rescue didn't fix it, the jobs would fall out of the queue. And so then we started trying to patch over that problem by looking through the queue and seeing what was missing and then adding it in. But that was sort of not elegant. It didn't feel all that good because we're constantly like scanning through the queue itself. So instead, the model that has worked well and has been robust is every so often look at all the servers that you need to examine or all the resources or all the formations and just plop all of that work into the queue whenever the queue gets to be a smaller size. So maybe add it over 3 times, and then once there's like 50% left, fill it in again. And then as new things come online, insert those ones manually. And that's worked extremely well. The one thing, though, that this causes with problems is is sort of problems with concurrency. And one of the problems that it took a while to reason about is, of course, when we were working an individual server, we would lock that server, and so no 2 jobs could be working it at once. But we were still running into weird concurrency problems. Excuse me. It didn't happen all that too often, but it was sort of dissatisfying that it was happening at all. And the thing that ended up solving it is this sort of semaphore pattern, where it's not exactly a semaphore in the like classical CS sense, but it shares a lot of the same properties. And so when we want to add a new server to a formation, this is sort of a simplified version of it. We do the work to add the server, so that kicks off a job to go and provision it, and then it does all the metadata work to add that server into the concept of the formation. But then each one of the individual servers existing servers needs to be updated to know about that new server so that they can do the cross-communication necessary in Citus. And so what we do here is we tell each one of those servers to increment by 1 their configure flag. And this is sort of an example of what would happen when the server's in the good available running state. Part of that is it looks to see if that configure flag is set to anything greater than 0, if it's positive. If that's true, transition yourself into configuring and save the changes to make sure that you actually got into that new state. And then in the configuring state, we do the work to reconfigure the servers to drop off on the new configuration files to give it the credentials and address of that new server, of all the servers that would include that new server as well, and then decrement that configure. The interesting thing is we're not necessarily setting that configure flag all the way down to 0. And that's because this is the sort of race condition that we didn't initially reason about. Because what could have happened in that sort of interim period of, okay, we realize that we've added the server and we need to do the reconfiguring, if another event came in that required reconfiguring, such as adding a new role to the system, a new username and password for customers to use, if a customer during that time clicked the button to add a role, that also requires a reconfiguring. And if the configuring step there, if all it did was say, okay, I'm done configuring, let's go back to running, there's a chance, depending on when that event came in, that adding that role would be lost. And so by doing it in this sort of somewhat more complicated way of incrementing the semaphore and then decrementing it every time we go through configuring, we can be sure that we've ran that configuring step at least once for each of the changes that needed to have happened. And the other thing that you need to do is make sure that if it happens, if it ordered in such a way that that first time through the configuring actually did take care of adding the server and the role, that the second time it's idempotent and it's just a no-op. And if you put those two things together, then you can have a very robust way to deal with these sorts of changes in configurations. There's a lot more details to this sort of semaphore thing. This is a blog post on our blog of how we use the state machines and a very long section on the semaphore thing. My colleague wrote, it's more of a book than a blog post. It was very long and difficult to read through. So the last sort of big concept here is storing metrics for our database service, both for showing metrics to our customers and for our own introspection and monitoring. And so one of the things that we do is give customer visible metrics. And most of these come from Amazon CloudWatch. But CloudWatch hitting the APIs on demand to get, to get these metrics, to get these dashboards is a little bit slow. So instead what we did was spin up our own Citus cluster to store all these metrics. And this is sort of what an individual row might look like. So we have the server ID, whatever the Amazon ID would be for that, what metric it is, timestamps, and then the actual data. And so what we're sharding by here is server ID. And so all of the metrics for an individual server will be on the same shard, on the same machine. And that's nice because in this sort of case, we're not really doing computation across different servers when we're pulling the data. We're really just getting the raw data, doing maybe some modifications, and then giving it to make a graph for the customer. Were we doing any sort of aggregation across servers, then maybe sharding on something different so that the data would be distributed across all the different cores would have been a better call. But in this case, the only thing we're using this for is showing graphs. The other thing is the primary key that we set up for this is the server ID, then the timestamp, then the Amazon ID, and then the name of the metric. And that's because it's sort of in that order that we're doing lookups on. And so having them all in one index speeds things up. And also, having all of those things in one index gives us a unique constraint so that we can't inadvertently add duplicates of the data in case where something goes wrong in that sense. The nice thing, though, what I didn't mention before about Citus is that this index is done on each one of the machines. And so once Citus routes it to the right machine, it uses the index just like a normal Postgres index, and it can get rid of all the extraneous data very quickly. The other thing, though, that's interesting is the admin dashboard metrics. And so we use an exception tracker, Sentry, for sort of runtime exceptions in our application. But one of the things that happens a lot is sort of exceptions that aren't, unfortunately, they're not exceptional. And one of them is a timeout error or a database connection error. Those happen all the time as the database is booting up. Like as we're doing those health checks to see, observe the state of the world, are you up yet, are you up yet, are you up yet? Those are generating errors. And we could just swallow them completely and ignore them, but there is some useful data there. So we were sending those over to the exception tracker. The downside, though, is that made the exception tracker really not useful. It would be pages and pages of these sort of expected errors, and then buried in there would be a real problem. And so we had this existing Citus cluster for the customer metrics. So we reused this and sort of put together this very simple exception tracker schema, where all it is an ID, a name, the timestamp, and then just a JSON column of whatever the exception is. And so by having that all together, we're able to generate this sort of graph. And here you can see something happened, something bad happened on Friday that caused a complete change in sort of the error profile for timeout error. Now, it's not a critical problem. If it was a critical problem and a database was down, we would be paged for that. But this is something to investigate. And so what we end up doing is, because all this data is there in the JSON-B, we can connect to this database, look at a few samples, and see if there's any patterns. And generating that graph is a pretty easy query of bucketing all the exceptions by hour, and then just looking at the last week group by name and hour. And there's a lot there that we could start doing. There's a lot of, I can imagine, having something that automatically notices through some, machine learning thing that, oh yeah, this pattern is different. Like, let's, send a message about that. And that would be really cool and fun to work on, but we haven't really needed it yet. So I've been, disciplined and haven't rabbit-holed into that. And this sort of ad hoc way of going in and just looking at example traces has been effective enough. I do want to share, though, one sort of misadventure that we went down. So we're using Linux as the operating system for all these databases, but we were really excited about ZFS. And we heard that ZFS on Linux is good enough these days, so we're like, okay, we'll try this. And the results that we were seeing were really impressive. We were seeing like 4 to 7, sometimes 10x compression on the data drive, and pulling all that over the network, because we're using all the network attached devices. I had really great performance with that data compression. And on the wall drive, we were seeing in some cases 70x compression, which was just really great. But then, sure enough, we started seeing some problems. We started seeing these memory allocation problems where it was trying, ZFS itself was trying to get memory from the kernel, and it was just like in some sort of tight loop. And it is a reported problem, and they'll probably get to it eventually. But unfortunately, we had to roll back off of ZFS. And I'm sure the Omni folks would say we should use BSD, but I think we're stuck on Linux for the time being, because of the experience that we have there. And that's it for all the prepared material. I'm willing to answer questions if you have any specific questions about Citus or about running cloud services for customers in general. But thank you very much. Yeah. Oh, bottled water. Yes, so the question was, we're using WAL files. Have we looked at bottled water? So just to make sure I'm thinking of the right thing, bottled water is the sort of Kafka, it sends the changes. So actually, I haven't myself looked into it, but some of my former colleagues were looking into bottled water and actually contributing to it. I think that is interesting. The use case, so I haven't looked at it as a use case for sort of the same thing that we're using Wally for not for. Sure. And so my main issue is like the data safety, number one. The nice thing about the bottled water is that it does automatically put the changes into a Kafka thing. What I'm not so sure about it is that actually easier than in your application putting the correct smaller amount of data into a Kafka thing or not? Like it's very interesting tech. I'm not sure where I would personally find a spot for it. I'm also not using currently. I'm not using Kafka, so that's the other side of it. But I think it is an interesting project, and I'm sort of keeping it in the back of my eye. But yeah, thanks. Yeah, so I mean, we started again from scratch, right? Like, because different things. But yeah, the main models that we reused conceptually was the having the separation between the server and what we give to the customer. Way back when it was just server, and putting that sort of seam in there between what we're running for a customer and what the customer's view of it is. Here it's formation and server. That is really powerful because we can replace the servers out from underneath and not have to disturb the customer. The timeline thing is the other big thing that we carried over conceptually, and that that allows treating the progression of data over time as a first-class thing. And so one of the things that we have there is we can put there our business rules around, this is the retention period in S3. Once the data is older than this, we can go and reclaim it. Or if there's no producers or consumers on that timeline, then we can drop that entire key space from S3. And having all of that logic into one encapsulated space that's been very valuable. Other things that we carried over, it was not a whole lot more. We were able to sort of take a second guess at things. One of the things that we did before was we ran on Ubuntu, and now we're using Amazon Linux. The reason for that was we were seeing weird kernel bugs in Ubuntu, and then we looked at who would be able to fix it, and even if we were able to reproduce and pervert it, and that there's not a lot of people, it seems like the Red Hat base, which Amazon Linux is a Red Hat based, has more core contributors and more, at least it feels like there's possibly a better way to get support. The other thing is, from Amazon, they're more willing to dig in and connect through the hypervisor over GDB or whatever to debug problems on their Linux distribution than other ones. And so we haven't been bitten by using Amazon Linux yet, or we haven't needed it. There's not enough data to know yet if that's been a good decision, but that's one of the big changes between the two. All right, thank you.